Okay, we'll now look at how exactly our envelope shortcut works with respect to our Lagrangian or constraint optimization problems. And here I'll follow the discussion from section 18.7 in the book. This is a generalized version, a very generalized version of the constraint optimization problems that we've been talking about so far. There'll be some extra notation in here, but just bear with me and I'll just simplify the result once I'm done with the discussion, the main discussion. So here, let's suppose we would like to maximize a function f, which is a function of n variables. So these variables x1, x2 through xn, these are our choice variables. And let's suppose we also have a bunch of parameters thrown into this function. And let us in particular assume that there are k parameters represented by R1, R2 through Rk, and we can summarize these parameters through the vector r. So basically you have a function f, which is a function of x1 through xn, and the k parameters are represented by the vector r bar. So here your function, the one you want to maximize, is a function of the vector x and the parameter vector r. And let's say you want to choose your x's so as to maximize f of x comma r, which are vectors here, subject to, and let's suppose we have multiple constraints here. Let's suppose we have m constraints, and the jth constraint is given by gj, the function gj, which is also a function of x and r. And let's suppose this is equal to 0. This is a constraint where j goes from 1 to m. Okay, so here also you can set up your Lagrangian accordingly. The point here is that when you calculate your optimum points, so we look at, let's say, any xi star that you calculate where I goes from 1 through n, that optimum point is going to be a function of the parameters. Okay, and once you plug the optimum points, xi is represented by xi star, into the function f, you're going to get your optimal value function, which is also going to be a function of r, because your optimal value function is such that you are in the function f, you are substituting instead of x's, if you substitute the points at the optimum, so that x star, which is also a function of r, and the parameters are already in here. So overall your optimal value function is also going to be a function of the vector of parameters. Now what the envelope theorem is saying, that if I want to calculate the derivative, just one sec, let me just see if this is being written. Yeah, this is fine. So the envelope shortcut is saying, what it is saying is that if I want to take the derivative of this optimal value function with respect to any one of the parameters, so let's suppose I want to differentiate this with respect to some parameter j, where j goes from 1 through k, because there are k parameters, then this derivative, so what this envelope theorem shortcut is saying is that if I want to take the derivative of this optimal value function f star with respect to any parameter rj, where j goes from 1 through k. Actually, let me use a different notation. I was trying to follow the book, but I don't want to use a notation j. So let's take some parameter, let's say t. Okay, so t goes from 1 through k. So if I want to calculate this derivative, I can just straight away calculate this derivative as the partial of the Lagrangian with respect to the parameter R sub t, where this result is again evaluated at the optimum. So your Lagrangian itself would be a function of the parameters R, and this has to be evaluated at the optimum. So this is nothing but partial L because Lagrangian itself is a function of x and r, and at the optimum x would be a function of r. So it will be partial L by partial R